All right, well, this might not be the best angle, but I have to do it. Yeah. Oh, yeah, yeah, that's where you start. Because that shows where you have to get to.
So is this good?
Yeah. Okay, cool. All right. So then the side work, Jeff. So right, Ewok, side Ewok. So you start with this guy, and pretty quickly see how this works. So here, of course, you can take a 2 out, difference of squares. You end up with 2x. 2x plus 5, so 2x plus 10 minus 20. I think, right? 2x minus 10. So then you divide by 2 and you get this. Now again, there's 2 things I want you to get used to. The form of the proof, which is a very basic proof, and keep in mind the idea of epsilon and delta are how we keep track of the idea of close. Right? It's a very important idea throughout all of mathematics, is what does close mean? Right? So one way to kind of deal with that is this idea of the epsilon and the delta defining close. So then over here, that's all my side work. So given this, we need to show blah, blah, blah. So given epsilon greater than 0, let delta equal epsilon over 2, from what we did over there. Then, if x minus 5 is less than epsilon over 2, 2x minus 10 less than epsilon, 2x plus 10 minus 20 less than epsilon, and then like you pretty much just go multiply by x minus 5. So you recapture this. That would be an appropriate level of work to show. And then we're done. That's what we needed to show, and we showed it. We're done. I like it. It's not that bad, right? But again, I don't know if everybody heard this. If you look at example 4 in section 2.4, just to give you a feel for like the next level of this. The minute that thing where I'm working with is not linear, and some of you guys might go, well, this wasn't linear. Well, yeah, it is, right? When you reduce it, it's linear. If it's not linear, things get much more difficult. All right. So that level will be on the quiz or a test. Just level of problem. I like it. Okay. Any questions about that? Was there any where you got hung up? That went pretty well? Okay. So later in the semester, when I say when the book references epsilon and delta, you'll know what they're talking about. Especially after you do the homework, you'll have a little bit more intimate connection with what the hell they are. Hopefully. Bless you. So I brought up this idea of continuity earlier today, and we talked a little bit about continuous before. We actually gave the full requirement for something to be continuous at some point. So for a function f of x to be continuous at a point A, what has to be true? I'm going to write it 3 things, and then I'm going to write them all at once. So for a function to be continuous, well, first off, the limit has to exist at that point, right? If the limit doesn't exist, then that's a big problem. There's no way it's going to be continuous. A really not good enough definition, but a decent one to get a feel for it, is continuous means I don't have to pick up my pencil to draw, right? If there's a hole there, I got to pick up my pencil to jump across the hole. If it goes to infinity, I got to pick up my pencil to come wherever the hell else, right? You with me? So that's really a little too basic definition, but at least it gives you a feel for what it is. So in order for the limit to exist, what's got to happen? The limit from the limit from the left and the right have to agree. So the limit as x goes to a of f of x from below has to equal the limit as x goes to a from above. The limit as x goes to a of f of x. Let me say this. F of a has to be L, right? And the limit as x goes to a of f of x has to be L. So to be completely honest, so this captures everything, but you don't need all of these. To be honest, this has everything in it. So the right and the left-hand sides have to agree. The function at the value has to equal L, and the limit that these both agree on has to be L. So they have to look like they're going towards L. They have to get to L, right? That's what that's saying. This last one, though, to be honest, covers everybody. Because the only way that the limit f is L is that the two sides agreed, and they agree on L. You guys kind of see what I'm saying? Equals, let me say it like this. This is even better. Equals L. So a way to capture all of these, here's the best way to capture all these, is to say the limit as x goes to a of f of x equals f of a equals L. Whew. I like it. It's not only does it have to look like, so at A, it has to look like from below and from above it's going to L. It has to actually get there. That's pretty much what it's saying. Yes?
Is this a scenario where 1 and 2 are true but 3 isn't?
Say again?
Is there a scenario where 1 and 2 is true but 3 isn't?
Oh, totally. They both agree. And f of a is L, but I never said that they agreed on L, right? Yeah, I like it. I think that's, to be honest, I didn't even look what the book says. Blah, 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 pretty much, okay. So here's a cool one. Let's bring in piecewise functions. This is where this kind of thing can happen really easily. Yeah, I'll make one. Let's see. All right, so one of the things going in that we should know for this is any polynomial function is going to be continuous. In fact, some algebra books actually say that before they really explain what the hell continuous means. So that's one reason why we classify polynomials. They're just so freaking nice. I'm working with a polynomial. Oh, thank God. Nothing freaky's happening with that thing. There's nowhere it goes infinity. It doesn't do this weird shit. Or it does go to infinity, but it's not as well behaved as it goes to infinity. It's not one of these suddenly goes to infinity out of nowhere. So polynomials are all continuous everywhere. So what's the only places this could be discontinuous? This kind of came up earlier today. Where are the only places I have to investigate for this? Yeah, at the connection points, right? At the points where I change trains, right? I'm on this train up to 1, and then I change trains, and then I change trains. Which train do I have to leap really far across to get to? That's going to be the one that's going to be free, right? So how do I investigate that then? What do I do? So what's the limit as x goes to 1 from below? You see if you guys can use this information appropriately. Yeah, how do you figure that out? Yeah, so below 1, which part do I use? This guy. So 1 minus 2 is negative 1. What's the limit as x goes to 1 from above? And which one are you using now? Yeah, this guy. What works for above 1? And why do I not care about this guy? Because I'm getting closer to 1. So of course, close to 1, this is the one that would work. And when I plug a 1 in there, I also get negative 1. So it looks like it's continuous at negative 1. Because not only does it look like it's going to negative 1, it actually gets there. How are we doing so far? Is that? Now look at 4. What's the limit as x goes to 4 from below? 5. Which one am I using? Of course, this guy, because below 4, that's the one that works. So the limit as x goes to 4. Is anybody freaked out about the fact that I can't use 4 for this? Why doesn't that matter with shit? Because the limit never gets to 4. So I'm just talking about things below 4. That's what this guy's all about. So that wants to go to 5. And what about the limit as x goes to 4 from above? 16. Oh, shit. So it's discontinuous at 4. So at 4, this function is discontinuous. To be specific, this type of discontinuity makes complete sense. They all do, actually. But as they go to 4, from below, it goes to 5. And from above, it goes to freaking 16. This would be a jump discontinuity. Don't you love that shit? That's a jump discontinuity, because it goes, jump here. Physically, that's, teleporting shit. We all wish, but no. Right? How are we doing so far? There are a couple other types of discontinuities. Let's talk about the types right now. We have jump discontinuity, which is easy. Whew, that word just keeps going. Jump discontinuity is exactly what it sounds like. What if I said removable? Which I love the name of this. The name of this one sounds exactly the opposite of what it should be. It's not removable, it's fillable, right? So another way to have a discontinuity is not just that you go here and then you pick it up there. It's also that you look like you're going somewhere and you never get there. So if I drew this for you, you see why they call this removable? And you see why I want to call it fillable? If you just defined f of a to be L, boy, it's my fifth puberty, that would remove the discontinuity. So if it's discontinuous, but it's not because it's a jump, but because it just never gets there, that's removable. Sort of like saying I remove a pothole by filling it in. Are you guys see why I don't like the name of it? It's not quite right. It's not removing the hole. It's filling the frickin' hole in, right? Well, we go, all right, I see what you mean, math people from the past, right? So we got jump, and we got removable. What do you think the third kind is? Discontinuity of the third kind. Sorry, I just got images of you guys constructing things out of mashed potatoes. You guys seen the movie Close Encounters of the Fourth Kind? The mashed potatoes? No, okay. What do you think the third kind might be? What's another way to be discontinuous? Yes, beautiful. Infinite discontinuity. Whoa. That's going to be where you have maybe. So it's discontinuous there. They don't connect, right? You can say, well, they connected infinity. Well, no. There's that wall. It's a trap. Let me see if they agree with me. Yes. Removable, infinite, and jump. They're on page 116, some more pictures of it. Blah, blah, blah. Oh, now watch. I want to show you an example of a function where it's a little unfair to talk about continuity at a certain point on it. So then we can make a little more broad idea of continuity. So the square root function. Would you say the square root function is continuous? Yes, totally, right? Except there's a problem. Here, a little bit of a problem. Every point on here, the lower one agrees with the upper one, and they actually get there, right? What's the problem here, of course? If you try to approach it from below, you're screwed. You shouldn't. That's like a technicality. It's like, okay, we can be better than this. So we have this idea of left and right continuity. So this is continuous from above, right? I have to be able to define that to make it fair. It's not fair to say it's discontinuous at this point. That's not fair because it doesn't exist past that point. That's kind of evil, right? Well, Larry's not here. Well, he's dead. He doesn't exist anymore. Give him a break, right? All right. Let me see. Oh, that's on the bottom of page 116. They talk about continuous from the right, continuous from the left. So you would be, let's make this more general, a f of x. Continuous from the right means that the limit as x goes to a from above equals f of a. And sure enough, as I approach 0 from above, the limit is 0 and the function value is 0. So that makes it fair if we're talking about these poor little things with restricted domains. Otherwise, it's not really fair. So you can have limit, you can have continuity from below, from the left, same way. I like it. Oh, beautiful. All right. So there's a couple of key theorems in a row. I kind of hinted at one of them earlier. There's a theorem that states, this is on page 118. This is a better theorem. Here we go. 120. I'm not going to write this all down. Now let me ask you this. What do you think about this phrase? Continuous on their domain. So if I ask you, is this continuous? What would you say? Is that function continuous everywhere? No, that function is discontinuous where? But is 2 even in its domain? No. So to be fair, sort of like we were fair for this guy, we could be fair, and we say it's continuous at every point on its domain. So so rational functions are continuous at every point on the domain. So it's continuous everywhere except x equals 2. Yeah. So we say it's continuous everywhere on its domain. So rational functions, polynomials, trigonometric functions, root functions, logarithmic functions, exponential functions, all these nice functions. Basically all the functions you've seen so far, really, right? Logarithmic, exponential, trigonometric, polynomial, who did I forget? Root, rational, even, absolute value functions are continuous on the domain. Right? Okay, so basically all the functions you've seen so far, for the most part. Piecewise functions, well, they can do whatever the hell they want to. They're always kind of weird. Couple that theorem, the theorem with all those types of functions listed, saying they're continuous everywhere on the domain, couple that with this idea. Continuity across algebra of functions. So if f and g are continuous, then so is f plus g, f minus g. This is on page, let me save myself some running. Bottom page 117. C, F, and C, G. What am I forgetting? F, G. And then, of course, the infamous F over G, as long as G does not equal 0. That's kind of taken care of. Those points wouldn't be in the domain of it anyway. So we kind of carry that over. So if I had this function, is this function continuous everywhere on its domain?
Yes.
Yeah, because it's composed of trigonometric, polynomial, logarithmic. So any combination, any linear combination of continuous functions is still continuous on its domain. What would be the domain of this thing? Don't overthink this. What's the only thing up there that has restriction? Does this have a restriction? What's the sine function look like if you graph it? And how long does it do that for? So it's infinite domain. Any problem here? No. You can square anything you want to. Here, what's got to be true? What's got to be true about x?
Positive?
Yeah, x has got to be greater than 0. Positive. I love it. You guys remember that? If exponentials look like this, logarithmics look like that. So asymptote at 0, so they have to be greater than 0 inputs for it to work. Okay, maybe. Blah, 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 blah. All right, I think we're at a point where we can do this. On the back side, I think, of that, yes, cool. These guys here, see if you can do those.